Our first speaker will be Sarika Jalan. Please, Professor.
Yeah, hi. Thanks. So this is my first time. I am in Latin America, Brazil. So it's a short visit, but so far everything very good, and I'm really enjoying being here. So thanks the organizer for having me here. So let me start without wasting further time. So today I'm going to talk about this couple dynamics on higher order interactions. So pairwise has been in the business for quite a long time, and today I'm going to devote next 1 hour that as soon as you incorporate higher order interactions, like which Timoteo Carletti introduced yesterday, then the emerging dynamics or synchronization behavior, how it gets impacted because of the higher order interaction. So that is the motive of my today's presentation. And I'll take one example of coupled Kuramoto oscillator to demonstrate this effect. So coupled Kuramoto oscillator, which is a very simple phase oscillator, I will introduce that. And this work has been done in the collaboration with my two young PhD students, very bright PhD student, Priyanka, Ayushi, and of course, this Bhuvan. And today I'm going to focus something which is beyond pairwise interaction. I am Sarika Jalan from Indian Institute of Technology, India. So it took like 30 hours for me to reach here, the very long journey for me. This is my web page and Google Scholar, my email ID. So before I start my presentation, let me do a bit of advertisement for this NetSci X conference, which is first time actually is started in Brazil. I realized just now, like this morning, that this first edition was in Brazil. And now this is the first time it is coming to India. So next year it is 2025, it's in India. This is the website which is already in place, and it's going to be, I hope it's going to be very nice conference. So please come visit us during that conference. So with that, let me now start the. So higher order interaction, Timoteo has already introduced this very well nicely yesterday. So today I am going to focus only on the simplicial complex, which is the one type of higher order interaction. Simplicial complex is nothing but the clique of order n. So here you can see it is triangles means clique of order 2. So all these three nodes are interacting with each other. This is clique of order 3, clique of order 4, which is known as 3 simplex. This is 1 simplex. Pairwise interaction is 1 simplex. So networks or graph, they capture only pairwise interactions, whereas functions of many real-world systems, and I'll take one example to demonstrate this, that functions of many real-world systems, they have been realized in recent few years that they are governed by the something which is beyond pairwise interactions. Like one example which is very easy to understand, like which is a social example of co-authorship networks. So suppose there's a paper. Suppose you want to create a graph of co-authorship. It means if two authors have written a paper together, so authors are the nodes, and if two authors have written a paper together, you put a link. Okay, so that's the way you construct a co-authorship graph. But suppose 3 authors have written a paper together. Your network doesn't capture that, because if you're saying that A, B, C, they have written paper together, then if you put a connection between A and B, another connection between B and C, and another connection between A and C, that is a pairwise. But that paper is the product of 3 authors. So that is one example of higher order interactions. Like, so you don't have A, B, or B, C interacting pairwise, but you have 3 authors interacting simultaneously in that graph. So you have pairwise interaction as well as triangle interaction there in that graph. So that is one very popular example. And it has been realized actually several places, actually. Last 3-4 years have seen actually a spurt in the activities of this higher order interactions. So it has been shown that in human brain, you have this enclosed cavities, and that plays a very important role in the information transmission. And then you have this empirical paper using the real data where they have shown this higher order link predictions. In ecological system, you have more than 2 species. They compete for the food or for the territory, and there also you cannot decompose into the pairwise interactions. So that is also example of higher order interactions. social networks, gene regulatory networks. So there are several actual examples, and there's one review article, which is, of course, I am also the author. So there are several review articles recently, but here I am just putting one, which is written by all of us. And there you can find many examples of real-world systems, which give the indication of the presence of something beyond pairwise interactions. Okay. So with this, now let me come to my phase oscillator model. So I want to demonstrate, as I was saying in the beginning, I want to demonstrate that as soon as I incorporate higher order interactions, how my synchronization behavior that can drastically change. And this I'm going to demonstrate using very simple model. This is one example. Of course, there are several other different kind of dynamical evolution people have shown recently. But I'll take very simple example of the coupled Kuramoto oscillator. And again, thanks to the morning talk, this has already been introduced. But let me now only focus on the synchronization perspective. So here, just be with me for some time. So you have this Kuramoto oscillator introduced by 1984 by Kuramoto. This is a simple phase oscillator. So theta is the phase of ith oscillator, and evolution of the phase of ith oscillator with time, that depends upon its frequency, intrinsic frequency, omega I. So in absence of any interaction, it will keep on evolving with this frequency, omega I. But then you introduce this kind of interaction. So now this is pairwise interaction, sine theta j minus theta I. So ith node is interacting with all the jth node because it's globally coupled. J is running from 1 to n. K is the coupling constant, and n is some kind of normalization. Okay, here this normalization is the number of oscillators. Okay, and in the weak coupling, it has been shown chaos, but I am not focusing there. My interest is synchronization, and synchronization means the definition of synchronization here, phase synchronization is theta I is equal to theta j for all time t greater than some initial transient. So I am focusing on the synchronization, and such kind of model, as someone was asking that in the morning, the one comment has come that we show this Kuramoto oscillator for fireflies. So I have some other examples for this Kuramoto oscillator. So there are some applications to the power grid system. So this is just the motivation that why I am taking this Kuramoto oscillator model. So this has been shown to very well apply to this power grid system. Of course, a variation of this coupled Kuramoto oscillators. Okay. And there are other examples, which is for the brain. So there also people have tried to model brain using this simple coupled Kuramoto oscillator. So instead of global coupling here, you have some weighted adjacency matrix, which is there. So there are some few examples just to show that this coupled Kuramoto, a very simple model, have been shown to be utilized for such a complicated system as a power grid and brain. Okay, so that is just for the motivation for the coupled Kuramoto oscillator. So let's see what happens. So now let me just spend some time with how synchronization happens in this simple one-dimensional phase oscillator. So because of coupling, you see, so you have some order parameter, weak coupling you have chaos, and strong coupling you have synchronization. And there's a measure of synchronization, which is this complex order parameter R e to power I psi. So it's very easy to see here that if all theta j's are equal, then you take mod of both sides, then R becomes 1. So when all thetas are equal, you get, so R lying between 0 to 1, because thetas are between 0 to 2 pi, so it's very easy to see that R is lying between 0 to 1. And for complete synchronization, R is equal to 1. Otherwise, it is 0. So if thetas are homogeneously distributed between 0 to 2 pi, then your R will be 0. And if all thetas are equal, then this R would be 1. So R is the scalar quantity, which gives you the magnitude of the synchronization. And psi talks about the mean phase. So psi is nothing but the mean phase of all the oscillators. And then how these oscillators behave as soon as you introduce this coupling. So when you don't introduce the coupling, depending upon the initial condition and the frequency, if frequencies are different, you will never achieve the synchronization, correct? So you have two oscillators, two are having different frequency. Irrespective of whatever initial condition you start with, you will not attain the synchronization as a definition that for all time t greater than some initial transient, you will never. But as soon as you introduce the coupling, something very dramatic happens, and that's why these Kuramoto oscillators become actually very popular, because you get some kind of phase transition. So here you see you increase the coupling strength. Below some critical coupling, R remains 0. So here what is plotted? X-axis is nothing but the coupling strength, and Y-axis is order parameter. And you can see that until you have increased the coupling strength until some critical point, R remains 0. And then something dramatic happens with the supercritical bifurcation. So here bifurcation is critical point which arises in such a simple oscillator model. So this is supercritical bifurcation at which R is equal to 0 state becomes unstable. And you have this bifurcation which is supercritical pitchfork supercritical bifurcation, and you have very smooth transition to synchronization. So what happens? The oscillator which follows such kind of relation. So the oscillator whose intrinsic frequency is close to the mean frequency, first they start getting cluster, then R is increasing, there's a feedback phenomena, more and more oscillators become logged, and slowly you get the global synchronization. So that is the mechanism for the synchronization, and very nice paper which I would recommend all of you, written by Strogatz, appeared in FISCA D, which talks about so many different mathematical actually complexity and curiosity which lies with such a simple Kuramoto oscillator. So this is with the pairwise coupling. Yes, please. What is? K is the coupling constant, and R here is the order parameter. So in the beginning, when R is very small, you can see that very few oscillators which are very close to the mean frequency, right now the mean frequency is 0, they will get synchronized. But as R will keep on increasing, you will have more oscillator which keep on satisfying this condition, and more oscillator will keep on getting synchronized. So it's like feedback kind of thing. So now synchronization, why synchronization? Because you have, this is already you all know, so, but still since I have a slide, this is the universal phenomena, and very nice book written by Pikovisky, Rosenberg, and Kurth in Word Scientific, if I can remember, but there's a very nice book written by them, and then you have so many different examples of synchronization, and of course we all want to understand, all nonlinear dynamics people are interested at some point to understand synchronization. So now you can see I have plotted simple this phase oscillator. There are two oscillators, omega 1. So first oscillator has intrinsic frequency 2, and second oscillator has intrinsic frequency 0.5. And if there is no coupling, what happens that they will keep on, so if I run this simulation, if no coupling, then you can see they will never get synchronized. They keep on moving with, this is not working, why? No, this is not, I don't know why simulations are not working. Actually, they should start moving like that. Yeah, they are moving, okay. So when there's no coupling, they start moving, and then they get saturated. Actually, the simulation is stopping here somehow. Video is stopping here, but they keep on moving in unsynchronized manner, okay. But as you have some coupling, I think with video, I think this thing has some problem with coupling, yes. So as soon as you have some coupling, you can see blue, and you have same oscillator, but as soon as you have coupling, then they start moving. But I don't know why this video has the problem. It is not, it is just getting stopped here. It is not. Yeah, so they should actually move at some point, they should get phase logged. Actually, they got phase logged here. It is moving, but very slow. So you get some phase logged, so you have to now believe on whatever I am saying, actually. So then for the stronger coupling, actually, they will get synchronized. So both of them will merge together. It is not working here. OK, it seems to work now. So they start actually coming closer. It's the same oscillator with the same intrinsic frequency, but based on the coupling strength, K, they are coming closer and getting synchronized. And this is now n number of oscillators. So here, let me now explain this graph nicely. So you have green dots are nothing but the phase oscillator with having some intrinsic frequency distribution. And this red line is nothing but the R. So here I have plotted both things, the phases and R. So length, that decides the scalar quantity, that decides the R. And now let me run this simulation. I hope this simulation should work, because it's a very beautiful simulation. Let's see. yeah, oscillators are moving. This is, I don't know why these simulations are not running here so nicely. Otherwise, they will start moving as you keep on increasing the coupling strength. It's stopped here. You will find that this dot will keep on increasing, and you have R that is slowly changing and becoming 1. Yeah, it is now, I don't know, there's some problem, but this is keep on moving, and slowly it is always showing very beautiful. I don't know why here the simulations are not working. But they will keep moving, and then finally they will get synchronized, and they will still keep on moving depending upon the mean frequency. If mean frequency is 0, they will stop. But if mean frequency is non-zero, they will keep on moving with the very nicely this thing. So now let me come out from these videos because that is hampering the flow completely. So I have shown this is for pairwise coupling. You get such kind of synchronization, which is a supercritical pitch 4 bifurcation. Okay, and here this is the one route to the synchronization. Now what happens when we have higher order interactions? So you have phase oscillator, Kuramoto oscillator, same. And what I do, I combine this thing with the higher order interactions. Instead of pairwise, I take higher order interactions. So couple Kuramoto oscillators on simplicial complex. And this is one of the example how one can incorporate that higher order interaction. There can be several ways to incorporate this higher order interactions. But here you can see instead of pairwise, instead of J and I, now I have another term K. And this is a nonlinear coupling. So it means this higher order interaction, triangle interaction, cannot be decomposed into the pairwise interaction. That is very important. You cannot have linear coupling here, which would be decomposed actually into the pairwise. Right now it cannot be decomposed. So now instead of having pairwise, you have intrinsic higher order coupling. And this is a one way of incorporating that kind of coupling, and you can have several other ways. And I have chosen this because of analytical simplicity. So here you can see BIJK is your hypergraphs. Here, since I have taken globally coupled networks, this will actually come out, actually, and you have running from J is equal to K, JK is equal to 1 to N. Lambda is the coupling strength, which was K in the earlier slide. And this is, again, some normalization constant, which you can forget right now. Okay. Now, again, you have some normalization constant. Right now, this is nothing but the average degree of simplicial 2. But this is a normalization constant. So when you have all-to-all coupled network, this is nothing but n into n minus 1, number of triangles in the network. So this normalization constant is nothing but the average number of triangles in the network. So for pairwise, it was n, but when you have globally coupled network, it would be n into n minus 1. So now what do you expect when you have higher order interaction? What kind of synchronization do you expect? So in the pairwise, you saw that as I was increasing the coupling strength, you have very smooth transition to synchronization through some kind of supercritical bifurcation, which I have not demonstrated, but I will show you later also the stability analysis. But now what kind of synchronization you expect? If I increase this coupling strength, what do you expect? The same system, you have same intrinsic frequency distribution. But instead of pairwise, you have triangle interaction. Any guess? Same thing? Okay. So I show you the result here. So nothing happens. You keep on increasing. So here again the same graph. K. So I am sorry for this one. I am intermittently changing lambda versus K. So K is the coupling strength, which is same here, which is lambda. So K2 versus R, which is plotted here. And you can see that you keep on increasing the coupling strength. And R is equal to 0 is the stable solution for all value of K. So you don't get any synchronization here. And the reason is that you have some kind of frustration in the system, which is not allowing to the formation of cluster. That is your hand-waving argument. But analytically, one can show that R is equal to 0 remains the stable solution, which I will show actually later. So R is equal to 0 remains the stable solution for all values of K in the thermodynamic limit. In finite system, you may get some kind of synchronization sometime. But infinite quantum limit, you will never get the synchronization. Then what is interesting here, why we are talking about that? The interesting thing happens that you have, this system is bistable. What does it mean? If you start from the synchronized solution, So when you start with the random initial condition, so the forward direction, you start with the random initial condition, and R is equal to 0 remains the stable solution. But when you start with a synchronized solution, so eta here is how many percentage of the oscillator you are starting with the synchronized one. So when you start with the synchronized solution, okay, and you decrease the coupling strength, the same coupling strength lambda, which now dramatically here is changed at K. So K2 lambda, it's all same. So when you decrease this coupling strength, you can see that there is this saddle node bifurcation, and you have desynchronization jump. So this is the explosive desynchronization which happens. So you have saddle node bifurcation. Since this is a numerical result, unstable orbit I am not showing, but later on when I have analytical analysis, then I will show also the unstable orbit. So right now there is one unstable point here which collapses with this stable point, okay? So you have saddle node bifurcation, and then you have this explosive desynchronization, and this is for different value of initial condition, which is not really, actually, you don't have to pay that attention on that part. So this was actually result which was there in 2019 by Skardal and Arenas in their PRL paper. So that was a big jump actually from smooth transition to the synchronization shown by the coupled Kuramoto oscillator to, so now you have subcritical bifurcation. Right now you have the saddle node, but you have bistability in this region. So two solutions are stable. If you remember, you can recall pairwise interaction, you have always only one stable solution, and now you have two stable solutions. So that is the criticality of the system have changed because of the incorporation of higher order interaction. And there are a series of papers later on by the same group, and then we started also working on at the same time. And we also showed a lot of different things, which I am not showing today because it's a 2-year-old work. I am going to show you something which we have done very recently, but last 2-3 years we have been working on. So we also shown with the Hebbian learning rule that it doesn't depend upon the initial condition, just to say that, but that is 2-year-old work. So now, what happens with, now I hope this simulation works because it's a very beautiful simulation. So left-hand side, I showed at how second order transition to synchronization happens, which is very smooth. R will increase very smoothly. Whereas the first order transition to synchronization, actually, desynchronization I'm not showing, this R will have very strong jump, actually. And if the simulation work, you will really enjoy this part because I like this one, but simulations, let's see, because now you see I am increasing the coupling strength. R is increasing, now it has stopped again. So R will keep on increasing slowly, and you all nodes, they will start forming the cluster. So if I again click, let's see, it's not showing. Yeah, it is only reaches to the final direction. But now here, the simulation has started, but you cannot actually enjoy the beauty unless it is running very smoothly. That there is sudden jump, actually. So here, R will keep on increasing slowly, and here there is sudden jump, which is not witnessed here. So, but I will share the slides, and you can see it in your computer, this part. So I will share the slides here. So it's not working here. But you will have that, what is the mechanism, and why one is interested in explosive synchronization, because there are several physical and biological systems which show such kind of abrupt jump, like in epileptic seizure, that is, of course, debatable, where there's a sudden jump from desynchronized state to synchronized state, and vice versa, that happens or not. So there are several real-world systems where such kind of bistability, actually, which I say bistability because you have two solutions which are stable at particular reason, that happens. So there are certain just example for the motivation part. And now, so let's again come back to the same slide. Like you have higher order interaction. I am not changing my model now. So here it was R1 I have plotted, and I will invite your attention to R2. So R1, that talks about the global synchronization, and whereas R2, it talks about two cluster synchronization. So if R2 is greater than R1, it means instead of global synchronization, you have two cluster synchronization. I will formally introduce this thing in the later slide. But here you can see R2 is greater than R1 in the same model. It means you have two cluster synchronization. And why two cluster synchronization is coming? Because of we have taken 2 theta I, actually. So if instead of 2 theta I, if I take 3 theta I, there will be 3 cluster synchronization. That one can understand using analytics, but I am just quoting this thing here that we have very good understanding that why 2 cluster synchronization happens. So this was the same slide, but now let me come to the current work which I want to present to you here. This is published this year only. And this is very nice piece in the sense that there are two different very popular methods in coupled Kuramoto oscillators, analytical method. One is introduced in 2008 by Ott and Tinson, that published in Chaos paper, and very beautiful, elegant way. They have, analytically, they have shown that how order parameter can be calculated. You can see that this is an n-dimensional system, correct? Theta I is running from 1 to n. So if you want to calculate R, numerically, either you have to evolve the system. Analytically, you have this n-dimensional system. So one has to do dimension reduction. And one can get some very close form of R that was shown by Ott and Tinson in 2008. So that is one analytical technique. Another one is using self-consistency method, which is very difficult because there you get very complicated integration. So there are two popular methods which are there. And here we have tried to solve this thing using some graphical methodology, actually, because this problem becomes very complicated. I will show you that how it is becoming complicated. So it is a very simple analysis, though these equations might look you sometime a bit complicated, but Ott and Tinson method is very simple to follow. And let me tell you, so now this normalization now, we have got rid of that complicated form because here you have all-to-all coupling, okay? So all-to-all coupling means how many terms, so we have to always normalize it with the number of terms we are using in summation. So earlier it was n for pairwise because n terms we were summing over. And right now the sum is going from j is equal to 1 to n and k is equal to 1 to n. So n square terms are coming here, and that's why we are dividing here by n square. And now it's a k2, which represents, k1 represents coupling interaction for pairwise interaction, and k2 represents the coupling interaction for two simplex or triangle interactions. So that is the terminology which I think I will consistently now use. And now instead of r e to power I psi, I have introduced this rq e to power I psi q. Not I, it has been introduced, and it is very well practiced in coupled Kuramoto oscillators. So q is equal to 1 means you have global synchronization. R1 represents global synchronization. And R2, that represents the two-cluster synchronization. So incoherent state means when R1 is equal to 0 and R2 also is equal to 0. Whereas global synchronization means R1 is equal to 1 and R2 is equal to 1. Because global synchronization, you have R1, R2, both will become 1. But as soon as your R2 is greater than R1, that is two-cluster synchronization. So from here, we can write down this equation in terms of the main field, okay? This is very easy to write down by substituting, by taking this thing here, by little algebra, one can write down this equation in terms of this main field. Now you can see in terms of this main field, you have R1, which is the global order parameter, psi1, which is the mean phase, and then you have theta I, and you have alpha here. So here you can see in the mean field, the oscillators are somehow decoupled with all the oscillators, and they are experiencing this main field, R1 and psi1. So this is one simplification, but still you have n-dimensional equation to solve, okay? So unless you do numerics, you cannot solve this equation, and then let me now show you that how Ott and Tinson, so we have just simply used the entire analysis which Ott and Tinson has done in 2008. So what they did, so you start with this mean field equation, and then you write down density operator. So here this density operator is F, and since number of oscillator remains same for entire time, so oscillators are moving, but this is a conservative system, so you know oscillators are coming in or out, so you can use this continuity equation. So density of oscillator with time plus del F theta dot d theta is equal to 0. This is simple continuity equation. And F here, it measures the density of oscillator with phases between theta and theta plus d theta having natural frequency between omega, omega plus d omega. So that is the density of oscillators in the very standard form, and this is a continuity equation. And now we can write down this continuity equation in its Fourier decompositions, because this F has the theta component, which is periodic in 2 pi, okay? So as soon as you have periodicity, at least in one component, I can always expand F in terms of its Fourier modes. So here now we have expanded here, F is the function of theta, omega, and of course at a particular time t. So I can always expand this thing in the Fourier modes because it is periodic in theta, so I can always write down, and now here you can see it was a function of theta omega t, whereas this Fn is a function of omega nt, and theta has come here. This is nothing but the normalization, because finally the total number of oscillator for all the time between 0 to 2 pi has to be equal to 1. So because of that normalization constant, you can get g omega is nothing but the intrinsic frequency distribution. So this is the normalization. From normalization, you can get this quantity. And this is a simple Fourier expansion. So now the problem has not become simpler, because now you have to calculate, and n is going from 1 to infinity. So you have to calculate infinite number of this coefficient and as well as complex conjugate. So when Ott-Intenson applies this kind of Fourier expansion, the problem has not become simpler. Now there comes the approximation which they introduce, and then problem becomes very simple, but that approximation works also actually very well. So the approximation was what? So that was the ansatz which was given by Ott-Intenson in 2008, that you write down this Fn omega t as a power of n. So now all n-dimensional stuff here, like infinite dimensional coefficient, they collapse to finding out only one coefficient v, because here n that comes as a power. And that approximation works in the complex plane where this v, mod of v has to be less than equal to 1. So that is the condition for this approximation. Now you can see that now you can substitute this thing here. So instead of infinite coefficient, you have only one coefficient to be determined, okay? So now you simply write down this continuity equation, and Fourier expansion of f theta omega t. From that Fourier expansion, you substitute here. Theta dot was nothing but, in the previous slide, you have that theta dot in the mean field. You already had the theta dot, if you can recall. So theta dot we are taking from here, okay? And f we are taking from that Fourier expansion. You keep it there. So let me now come to this slide faster, because of this animation, it's taking a lot of time. So you put it here, and then what you do, you equate the coefficient corresponding to e to power I n theta. And it happens that entire dynamics that collapses to this Ott-Intenson manifold. So you equate the coefficient corresponding to e to power I theta, e to power 2 I theta, e to power 3 I theta, and all this coefficient actually they collapses to the only one equation, which is known as Ott-Intenson manifold. Now here you can see this v, which was approximated in the previous slide. If you can remember, Fn was equal to v to power n. We got one equation for that. It consists of the frequency, which we know already. Z1 is the order parameter, okay? The complex order parameter R1 e to power I psi 1. And alpha is my phase constant. So you can see now entire thing has collapsed into one equation. So you have n-dimensional equation. From there, now we have collapsed to the one-dimensional equation, but still our problem is not resolved, because here we got some differential equation in V, but we want a differential equation for R, for order parameter, and order parameter is coming here. But now this problem is resolved, like as soon as you take R in, you take R for the, you write down R in the continuum limit and do some algebra, which is all there in the supplementary material of our paper. Then you get real and imaginary part separately. So take home message here is that now you can see that you get equation for R2 dot. And this R2 dot, you see, this is the time differentiation of R2 with respect to time. This is R2, this is K2, which is known to us. Psi 1, psi 2 is the mean phases, which we can approximate as 0 at certain point, but let's not do any approximation here, and alpha. So now you have two coupled equation which you have to solve, which you can solve very easily, and you can actually draw the entire bifurcation plot. So it means now you know how many solutions you are having, so you put R2 dot is equal to 0. You know how many solutions you are having. You can do stability analysis, linear stability analysis by writing the Jacobian at particular R2. So you know the stability and instability of all existing solutions in the space. So you have, so this R2 is equal to, this thing is the different solution. So you can see this is the fourth order. So you have 5 different solutions which you get. So, and then fixed point solution, this you have to believe in the rotating frame, psi 1 is equal to psi 2 is equal to 0, that happens. But now you can see using this Ott-Intenson approach you have n-dimensional equation that is collapsed to the two-dimensional equation, and you can draw the entire phase diagram. But here now you have calculated R2, and now few slides. Now under few slides are there where we have shown that how to calculate R1, which I am skipping because later on, if you are interested, you can go to the supplementary material and you can ask me, because there's some involved analytical calculation which we have done. And now let me come to the final point here. Like of course, we can get R1, but we can also got this mean frequency in terms of alpha. So the entire cluster, so you get two cluster solution. An entire cluster is rotating with this omega, and this omega that depends upon alpha. And getting this such a closed form that required some kind of graphical techniques, and of course, Ottentinson method, we took R2, but for calculating R1, because R1 is involved, we had to use the self-consistency method, which is also very well established. Nothing new there, but this graphical methods are a bit more, which has been involved there. So now you can see that the entire two cluster, and as a very neat, clean, we have got entire thing. We have solution for R1, we have R2, like how time evolution of R1, R2, and as well as the mean frequency omega. And here are some results which are there, which is actually same as was expected. In the forward direction, you won't get any synchronization because you don't have any pairwise interaction. Unless and until you have pairwise interaction, in forward direction, you will not achieve synchronization. So since there is no pairwise interaction, only the triplet interaction is there. In the forward direction, you are not getting synchronization. But the reverse direction means you start with the synchronized state, because synchronized state is a solution, correct? Then you can see as you are increasing alpha, it is shifting towards right direction. So this is the numerical result, which is also analytically one can see, because you have R1 dot equation, R2 dot equation. So you can completely, so this symbols are from numerical simulations, and lines, so there are lines also, which is from analytics. So numerical simulation and analytics are working very well for n large, because if you have finite size, then you might have a different result for finite size effect because of bias stability. But for n very large, right now 10,000, I think we got numerics working, matching very well with the analytics. So this is two cluster synchronization, because you can see R2 here is greater than R1, correct? So that is two cluster synchronization. With that, I think I am finishing this part, because I have one small part more for when we have pairwise interactions. So here the take-home thing, no forward synchronization with alpha backward critical transition point that shifts towards a higher value. And this is just one result, but the important point here is that we get two cluster because of the higher order interactions, and we get rotation because of alpha. So alpha is equal to 0, we won't get rotating cluster, because if you can see in the formula here, so as alpha is equal to 0, this mean frequency becomes 0, okay? So because of the higher order interaction, 2 theta I term there, we get two cluster, and because of alpha, we get this rotation. And you might, yes, please. Both solution means two cluster state is one solution, which is stable. Two cluster state is one solution, which is stable. Sorry? R is equal to 0.
Yes.
R is equal to 0 is stable until only the critical point. After that, R is equal to 0 solutions become unstable. So this R is equal to 0, that is stable until here. I see. Sorry. In the forward direction, it is always stable. Yes. Sorry. Yeah.
Yes, so they're both
So
stable.
R is equal to 0 is always stable for all k value. Yes, correct.
So what about the basins of attraction?
So basin of attraction corresponding to synchronized state, that is very small. So unless you start with the synchronized state, you always actually, so that is actually very laborious work to find out the basin of attraction actually. So I would say in one of our work, when we have multi-layer, we found one very small stable orbit between, like we got 3 stable solution, and so far we were not able to find out the basin of attraction, because analytically we can see the solution, and analytically we can know which is stable or unstable, but numerically, what is the basin of attraction? No, I don't want to
certainly believe that,
make any comment here. Yeah. Yeah, okay. So, yeah. So no forward synchronization, and with alpha, backward critical points shift towards the higher value. But R1 is equal to, so 2 cluster because of 2 theta I, and rotation because of alpha, okay? So this you can skip, that doesn't, this is just for the completeness. So now this is the conclusion only for this part, because I have few slides to show when we have pairwise interaction that what happens, because right now there's no pairwise interaction. So we analytically solve this impact of phase lag and explicit dependence of omega on phase lag parameter. So that shows that alpha can be used. Actually, for pairwise interaction also, I don't remember, but I don't want to claim whether such explicit dependence people have derived, but maybe there. But higher order, at least we have done it first time that I know. So, and this is the reference, and these are the other work where we have done for higher order interactions. With this, let me just show quickly that what happens when we have pairwise. But right now, I have taken out alpha, because alpha only makes the movement. As soon as you have alpha, you don't get non-rotating cluster. You always get rotation, whether it's a global or this thing. So that is the role of alpha. But now let's see what is the role of when you have pairwise and you have higher order, etc. Okay. So this is a pairwise, 1 simplex, 2 simplex, 3 simplex. What do you expect? Suppose now if I have pairwise also, now I am fixing K2, what will happen in the forward direction? Let's first talk, because reverse direction we see that synchronized solutions are there and there's explosive desynchronization. But forward direction, I showed that when you have only pairwise, you have supercritical bifurcation. When you have only higher order, you don't have any synchronization. But when you have combination of both, what do you expect? Same thing of what? Same thing like this or like this? Okay, same thing like, okay, so what do you expect, okay? Because let me try to give you some hint. So what is the role of pairwise? Pairwise try to bring the things together, try to synchronize. It favors the synchronization pairwise. Whereas higher order, it creates some kind of frustration in the system. Like, so what happens when 2 oscillators are there? So suppose one is pulling and one is dragging, and they come close together to the mean frequency, correct? That's how synchronization happens in the pairwise. But the triangle, theta 1, theta 2, theta 3, it doesn't know that which oscillator it should go. So there's some kind of frustration. So formation of giant cluster, that is so, K2 has a role of frustration, where K1 wants to synchronize the things. And any system, when you have a force which is trying to synchronize, and the force which is frustration. So what happens? K1 is trying to synchronize, K2 is trying to destroy, and suddenly, as soon as K1 overcomes that kind of frustration, you have sudden jump in the synchronization. So that exactly, this happens here. Actually, the system is running very slow, I guess, because it doesn't take so much time when I press and things to appear. This is the complex. This is all entire analytical calculations again, but I will come to you to the point which is important. So now, instead of now you have mean field, instead of only K2, you have K1 also appearing here into the picture. And I do the same Orton-Tinson method, which is very easy to actually do. You write down the continuity equation, you write down the Fourier series, you apply this Orton-Tinson approach, then you equate the coefficient both sides, write down that your R in the continuum limit, and then using the Lorentz frequency distribution, that works only for the Lorentz frequency distribution, because you get some integration, which you can solve only in the complex plane for the Lorentz distribution. And bimodal also I have seen, but for simple Gaussian distribution, the integration becomes quite complicated. You cannot solve it. So it all happens, and finally, actually, you get something in terms of R dot, actually. So alpha dot is still that. So now you get something in R dot. Now let's spend some time on this equation to understand. So here you see that as soon as K2 is 0, if K2 is not here, correct? And if you do a stability analysis for R is equal to 0 solution, okay? So if you do a stability analysis for R is equal to 0 solution, it means you write down del R dot del R. So here it becomes -1 plus K1 by 2, because this term will become 0, because R is equal to 0, you are doing the stability analysis. So what happens? K1 is equal to 2, it has become a stable solution, and after that K1 greater than 2, R is equal to 0 becomes unstable solution, which is very straightforward to see here, okay? So nature of, so critical points remain the same. That doesn't get affected by K2, because you can see it is having R cube. So even though you differentiate it once, it will become R square. So at R is equal to 0, this term is not contributing. So your critical coupling strength, that remains the same. But the nature, that changes actually. So this one-dimensional manifold is just telling you that K2 does not have any impact on the critical coupling strength in the forward direction. It only changes the nature. And nature, how you can see, you have to find out all the 5 solutions, because this is a polynomial of order 5. So you have 5 solutions. Okay, I show you how this is 5 solutions, because you can see only 3 solutions, but I show you how this 5 solutions. So these are the results actually. First, let me show you results. So this is for when K2 is equal to 0, and this is when K2 is equal to 10. So what happens? You start from K is equal to 0, K1 is equal to 0, and K2 you fix something. Exactly at K1 is equal to 2, you get supercritical bifurcation for K2 is equal to 0, but you get sudden jump for K2. So you get sudden jump. So nature of the transition that goes from supercritical to subcritical, okay? But critical coupling strength remains same. Now you start from the reverse direction, and then you can see that you have saddle node bifurcation here. So you have 1, 2, 3 solutions are there, but I'm saying there are 5 solutions because it's a polynomial of order 5. So where are other 2 solutions? Because you can see there are maximum 3 solutions. 1 is stable, 1 unstable, and another stable. Where the other 2 solutions? They are in the negative, not complex. They are in negative direction. So, so negative direction, because that is inadmissible. So we are not plotting that because they are in the negative direction. And actually we can show that when we have, so this is now negative direction, you see. So here also you get 3 solutions, but negative direction is inadmissible. So you have entire thing you can do with this Ott and tension stuff. And you can see that the role of higher order is that from supercritical you have subcritical. There is one more interesting thing which you can notice here, that you get synchronization even with the negative pairwise interaction. So in presence of higher order interactions, you get even the synchronization in the negative coupling strength as well. So something which was actually destroying the synchronization, you know, like higher order is somehow causing frustration. But you see, when system is synchronized, in presence of higher order, it's very difficult actually to break the synchronization. So that is something which is very interesting. And there is one more work which we have done in the multi-layer higher order interactions. And then we have shown here that you can get entire hysteresis and forward transition in the negative pairwise coupling strength. So that is only in the presence of higher order interactions. So with that, I finish my talk. So this is the future directions. So for whatever I have shown, this is for all-to-all. As soon as you take network structure, I know only one paper by Skardal where he has taken, that appeared in Journal of Physics Complexity, where they have taken correlated network. So that is for higher order. And pairwise also people have done, like Pinaki, Pal, etc. These Indian guys, they have done with the correlated networks. So except that, when you incorporate the network structure, I don't have any idea that whether you will get first order, second order, and when you will get, how sufficient frustration you have to have in order to get first order transition. Analytics is very difficult because now you had global order parameter, and for network structure, you have to have local order parameter. So analytics becomes very difficult. One thing which I have not spoken, but we have the results, very nice results. I didn't want to talk about this because this was not submitted. I wanted to talk about the published one. Finite size effect. So pairwise people know, but here the finite size effect becomes very interesting because you have bistability. So let me stop here because let us polish this result and we have submit. And then multi-layer structure, you have a lot of scope, like one layer you have higher order, another layer you have pairwise. Of course, you have to see the physical motivation, but at the model, at the toy level, you can have actually a lot of scope here. And this is the acknowledgement, my lab. And thank you very much for your kind attention.
So we have time for questions? Okay.
Thanks for the talk, very nice. So I have a question about the coupling that you use. So in the first part of the talk, you use a coupling which is symmetric, theta j plus theta k minus 2 theta I. And then in the second part, you use this asymmetric kind of coupling, which makes everything much, much easier, right? You can use the Otto-Antonsen ansatz and you get these simple equations. But how do you do that for the first coupling?
So that's what I made this comment in the beginning, that there can be several forms of the coupling. You're right. In one form, I take 2 theta I. So when we take 2 theta I, what happens when we apply Otto-Antonsen approach, we get the equation for R2 dot.
Right. Yeah.
And finding R1 dot is very difficult, actually.
But how do you do that for the first type of coupling? Can you use the Otto-Antonsen ansatz?
First type means this type of?
No, the other
2
one.
theta I, 2 theta I.
This is easy, yeah.
So 2 theta I, you can do the Otto-Antonsen approach, but you get the lower dimension manifold in terms of R2 dot, not in terms of R1 dot.
But you get an equation for
R1, for getting R1, we have to do the self-consistency method, which was very difficult, actually. Like, Otto-Antonsen is very easy. It's like a recipe.
Right.
You do that,
Yeah.
you get it. But when you want to do self-consistency, you get some very complicated integration because you have to integrate from those oscillators which are logged. So limits are actually very complicated. And it is like a self-consistent equation. Both sides you have R1, like this side also and that side also, because in the limit R1 comes. So it becomes very difficult to solve. Yes, you're right. And that's why we use always such kind of coupling, because yes, you're right.
So, but in the first part of it, so those equations that you showed, so they are the exact equations?
They are exact equations.
So you can work this out?
Actually, we solved it, actually. And why we could solve? Because there was no pairwise term. We had only this term.
The pairwise terms will make it difficult.
Yeah, because if you have pairwise term, no, we cannot solve. No, because pairwise term will give you the mode of e to power I theta.
Right.
Higher order will give you e to power 2 I theta.
Right,
so
exactly.
no, you cannot solve this.
No, okay, good.
No, it's very
but
difficult.
because I tried to do that.
No,
I
you
got
cannot.
exactly that
We spent so much time. No,
okay, good.
We had a very lot of time, lot of approximation. We also
okay, so I'm happy that I'm not
No, it's
too
very
stupid.
difficult.
Okay,
Because you have two modes simultaneously present. No.
Okay, great. Thank you. Thank you.
I have a very quick question. In the original model, in the original Kuramoto model, when you add the phase lag, it has to be bounded by P half, I think.
It has to be bounded by?
P half, P over 2.
Pi by 2. Yeah, because when you have pi by 2, then the sign becomes cos, and then you never get synchronization.
But
that is for pairwise. So for pairwise, there is this very good question. Why? Because in the pairwise, you have this Sakaguchi, Kuramoto original paper, they have written the expression for Kc, where it shows that it becomes infinity. Like critical coupling strength becomes infinity as soon as you have alpha is equal to pi by 2. But here, so here, when you have pi by 2, then what happens?
That's the question.
Actually, we did so many things, but I don't, pi by 2, I cannot claim here that you don't get synchronization. Because there you have analytically, Kuramoto, Sakaguchi have shown that you have in the denominator, you get something which makes this thing to blow up. Kc becomes infinity. So that expression I remember. So Kc becomes infinity there for pi by 2. But here, I don't know. You must have the results for numerically, of course, but I cannot make out that. Okay. Because none of the analytical expression is suggesting that. And you know, higher order interactions does something very different than pairwise. So we cannot rely whatever results are there with pairwise.
that's
So
what
no,
I was
I don't
asking.
know. I'll get you back with the results.
Sure.
We must be having, I have to ask these two
Sure,
young,
sure.
my PhD students, they must be having
Okay,
the.
good. Thank you.
Yeah. Yes.
Yeah, thank you very much. So once you have the double sum, do you exclude j equal to k, or do you consider? Because if you allow j to be k, you always have a pairwise interaction, even if you are thinking that you are removing them. Of course, with the different scaling parameters, I agree. Both in this case than in the previous case.
No, I didn't get your
So
question.
if you let j equal to
So
k
here
in the
doesn't
double,
matter. If you have j is equal to,
yeah, if j is equal to k, this is a pairwise interaction.
so only one term is pairwise.
Yeah, this is pairwise. This is theta j minus theta I.
No, but there's only one term which is
No,
pairwise.
you have n terms. For all j, there is one k equal to that j.
I see, I see.
And so you have again
So
a
you
terms
have-
that you add to the first one. Yeah, no, it's not a square. It's not be, you still have n terms, so it's n at most. Indeed, if you have k, k2 is 10 times k1 sometimes.
Yes, and you
So
have
if
this,
you isolated this
I have to see the
pairwise
codes.
interaction, it's
I
like a
don't remember.
Kuramoto with a very small parameter in front, so it will not synchronize.
What will not synchronize? Again, please.
Yeah, but if you write this term, you put with the first one, it's like if you have a Kuramoto pairwise with a very small term in front, then it will not synchronize by definition. So if you take a Kuramoto with pairwise, a k very small,
Okay, very small. Then
you don't have synchronization.
yeah, you may be right. I was just checking.
Then you
the
have
codes
adding
here.
two phenomena at the same time.
Yeah, whether we have, because we have to discard, yes,
Yeah.
I think.
It's just the way you write the sum, but in reality you remove.
Yeah, must be. Let me check the codes are there in this laptop only, actually.
I did a calculation similar to that. You see, if you write this sinus theta j
I'll check and,
minus theta
because
k.
you're right, because it makes K1 smaller, is it? Because K1, no, it is addition of one small quantity, because this term remains there. And then you have some K2 upon n square, some pairwise interaction. So how it is making K1 is smaller? N terms, but that is, so this is intact. This is not changing, correct? Now K1 you are increasing, then you have plus some small addition term. So K1 is that is 1 over n. So that is some addition to this term. So that is not making effective pairwise coupling smaller, even though if we take, incorporate j is equal to k, then also effective pairwise coupling is not becoming smaller. But I'll think over more on this. Yeah.
One more question? Two questions, okay. Two questions.
About the higher order Sakaguchi model, those cluster solutions, they are all rotating, or they are all stable, or do you have non-rotating cluster solutions that are also stable?
Okay, so as soon as you have alpha, this mean frequency, which actually when alpha is non-zero, alpha is 0, mean frequency is 0 actually. It depends upon the intrinsic frequency distribution. If you take symmetric frequency distribution, your mean frequency, like the cluster will not rotate. But as soon as you have alpha, always you have rotating cluster. So instead of two cluster, so two cluster is coming because of we have two theta I term. But if you have only pairwise term, theta j minus theta I, then you have only one cluster, but it will rotate.
And when you, the phase diagrams you show, the order parameter as a function of the coupling strength, you showed, I think, 2 examples. How do these diagrams depend on the phase lag?
This one?
Yeah.
So,
So I believe this is for a fixed alpha.
so this is as you are changing alpha. So alpha is equal to
okay.
0.
There's alpha.
You have explosive desynchronization. But as you are keep on increasing the alpha, you can see that critical coupling strength, you
Okay,
get desynchronization faster.
Yeah, I couldn't see if it
But
was
why you get
eta or
desync-
alpha, but it's alpha. Okay,
It's
thank you.
alpha. So here we can only show with the analytics that when you have what solution. So apart from that, yeah.
Is it done? Yeah, okay. It's a question that I understand what you do, but for me it's not clear why this is higher order interaction, in the sense that it's like having 3 pairwise interactions, but it's not really a group interaction.
This is not pairwise. You cannot decompose it. So suppose if you have a linear interaction, suppose if I write down xj minus xi, and then I make it higher order like xj plus xk minus 2xi, this you can decompose. You can write down xj minus xi, plus you can write down xk minus xi. But as soon as you have sinusoidal here, you cannot decompose into the pairwise, no.
Yeah,
Unless you...
That I understand, but the argument of the sine function is not really captured in the higher order structure, in the sense that it doesn't distinguish when the triangle is empty or is full.
Okay, so we have taken simplicial, but to resolve your concern, if as far as you have Bijk. So as soon as you have Bijk matrix, then that captures when a triangle is empty or filled, because then you have this higher order tensor, which says that when it is, so it is one only when your triangle is filled, otherwise that's empty. So I have not taken Bijk. But you can incorporate those things by taking corresponding adjacency tensor for the higher order interactions. Okay. Right now, I have fully connected, yeah. So I have all my triangles are filled. I have N, C, 3 triangles in the network. NC2 pairwise and NC2 triangles, and I have taken all of them here.
Yeah,
so,
okay,
so,
still, I don't know how to...
So if you have your adjacency tensor that incorporates, you can say that which triangles you want to take and which triangles you don't want.
Yeah, and the other question is related to the how you normalize the coupling constant. Mm-hmm. So in the original Kuramoto model, you have the n, because you need the n to make it analytically consistent.
So you have, you have n terms, because j is equal to 1 to n. That's why you have, you normalize with the number of terms. So this is simple average thing here. And now since you have 2, you take actually n into n minus 1 or n square, okay? Because j is equal to. So
no, but at some point you were divided by the average.
So that was when you have your hypergraph. So hypergraph, when you have, we divide. So when you have matrix, so traditional Kuramoto oscillator, so when you have Aij sine theta j minus theta I, so there are several ways people normalize it. One way they normalize either with the average degree, or they normalize with the degree of ith node. So this is 2 ways they normalize for the standard Kuramoto oscillator with the pairwise coupling. Okay. So if you take average degree, so in the similar fashion, if you have Bijk, then you normalize it by the average triangle degree, so which I have called D2 or D2 here. So here it is D1. This is the pairwise average degree. This is triangle average degree.
I know, but none of these solutions make the equation analytically solvable in the infinite time limit, because the sum is still scaling with n, and either the average degree is a constant, or the maximum degree is scaling with the power of n.
You define. So I know this work by people who have done only with the pairwise this thing and higher order by Skardal. What they do there, they define the local order parameter, which is something upon 1 upon ki summation over I theta j, Aij. So there people work with the local order parameter.
Yeah, and
and
that
then-
has a problem that you are homogenizing what is inherently
yes.
heterogeneous. You are including that in the equation, so you are homogenizing something that is, so essentially you are kind of washing out the heterogeneous character of the topology because you are,
So I have never done work with network. I just know the people who have done, and they have tried with this kind of local order parameter, and then Aij is correlated, then you can write down the continuum limit. So similarly, in the Skardal work also, they have done in the similar fashion. He has defined this thing with local order parameter, which is actually 1 upon whatever e to power I theta j plus theta k, actually. So, so people have tried to do. I know just 2 works for them with but we have never done work with because it becomes.
So let's thank Sarika again.
Thank you. Thank you.
We have a coffee break now.